Okay, let's unpack this. We're diving deep today into a topic that's just absolutely crucial for Europe. Climate goals, industrial future, you name it.
Yeah, it touches everything.
We're talking about how to make steel production green. I mean, steel is everywhere, right? Buildings, cars, even the washing machine.
Absolutely essential material.
And the industry itself, it's a cornerstone of the European economy. But, and it's a big but, it's also responsible for a pretty significant chunk of the EU's CO2
A
emissions.
really big chunk.
So the question is, how does Europe actually move away from coal-based steelmaking? And maybe even trickier, where should this green steel actually be produced? For efficiency, cost effectiveness.
That where question is key.
Exactly. We've got a fascinating source to help us navigate this today. It's a study titled Towards Defossilized Steel, Supply Chain Options for a Green European Steel Industry. We're going to pull out the most important nuggets from this research, give you a shortcut to getting up to speed on this really complex topic, and see what this study suggests about, well, the future map of green steel in Europe.
And what's great about this study, I think, is how practical it is. It's not just about the tech, the how of green steel.
Right.
It really digs into the where and the how much. It models the actual economics of different supply chain setups.
Okay.
Across Europe, yes, but also looking at potential import partners. It's trying to figure out the most cost-effective ways to get green steel where it's needed. And not just for tomorrow, but looking ahead 2030, 2040, even 2050.
Long-term view.
Exactly. So we'll walk through where things stand now, look at the main green alternatives, and then dive into what this study's number crunching reveals about costs, about the implications of these different supply chain choices for three actually quite different key European countries.
Okay, so let's set the stage first. The scale of this challenge, it's pretty massive, isn't it?
It really is. Steelmaking alone is responsible for about 4% of the European Union's total CO2 emissions.
4%, just from steel. Wow.
Yeah, that's a big slice of the pie that needs shrinking if Europe wants to hit its climate targets. And Europe isn't some small player on the world stage here either.
No, it's huge. Second largest producer globally, right?
That's right, about 8.5% of world crude steel production. So cleaning up steel here, it has real global ripple effects.
And what's the root cause of those emissions? It's the way we make most steel now.
It really comes down to the technology. The bulk of EU steel, maybe around 60%, still uses that traditional method. The coal-based blast furnace plus the basic oxygen furnace, the BF plus BOF route.
Right, the old way.
And that process is just fundamentally tied to burning coal, lots of it. The emissions are incredibly high, I think around 2.25 tons of CO2 for every single ton of crude steel.
2.25 tons of CO2 for 1 ton of steel.
Yeah. And even if you clean up the electricity used elsewhere in the plant, the core chemistry needs that fossil carbon. So emissions only dip slightly, maybe to 2.06 tons. It's a classic hard-to-abate sector. Incremental tweaks won't get you deep decarbonization.
Okay, so BF plus BOS is the high-emission incumbent. What's the main green alternative that this study is really focusing on?
The main path forward being pursued, and the one they modeled in detail, is using hydrogen for direct reduction, then feeding that into an electric arc furnace. So HDR-EAF.
HDR-EAF.
I got it.
And the fundamental change here is swapping out coal for hydrogen. Hydrogen becomes the agent that strips the oxygen from the iron ore.
Okay, so using hydrogen instead of coal.
Exactly. But critically, for this to be green steel, the hydrogen has to be green too, produced using electrolysis powered by renewable electricity.
Right, green hydrogen.
And the electric arc furnace, the EAF part, that also needs to run on clean, renewable electricity. So you're basically shifting the whole energy dependency from coal over to clean hydrogen and clean electricity. And the pressure to make that shift happen is definitely mounting. The EU Green Deal targets, at least 50% GHG reduction by 2030?
Compared to 1990 levels, yes, and 2030 is coming up fast.
Really fast, 6 years. That timeline means we need huge, rapid changes in steel. And this HDR route seems to be what everyone sees as the key.
Absolutely. And, despite the enormous challenges, technical, economic, building whole new plants, scaling up green hydrogen.
It's a massive undertaking.
It is. But this study highlights that things are starting to happen on the ground in Europe. We're seeing big players move past just pilot projects.
Like who?
Well, think ArcelorMittal with plans for HDR and EAF conversions in Germany and Spain. ThyssenKrupp is building an actual HDR plant in Germany. SSAB is doing collaborative work in Finland for fossil-free steel. These aren't just ideas anymore, it's investment in physical infrastructure.
And that lines up pretty well with the EU's own hydrogen strategy, doesn't it? The targets for electrolyzers, promoting hydrogen use in industry.
Exactly. The strategy aims for 6 gigawatts of electrolyzers by this year, 40 gigawatts by 2030, and it specifically calls out using hydrogen in industry, including steel, from 2025. So yeah, the policy direction and the industry moves seem to be starting to align, even with those big investment hurdles still there.
Which brings us right back to that critical question the study tackles. If we have to build all this new green capacity in the HDR plants, the hydrogen production, where does it make the most economic sense to actually put it?
That's the absolute core of their supply chain analysis.
All right, so towards defossilized steel, supply chain options for a green European steel industry. It wasn't just about the tech. It modeled the economics of different ways to get that green steel or its components to the market. And they picked 3 specific countries.
Yeah, 3 case studies to represent different European situations. Germany, obviously, the biggest producer. Spain chosen because it already has a lot of EAF capacity and, crucially, great solar potential.
Good sunshine.
Exactly. And Finland, representing Northern Europe, different renewable mix, different context.
Okay. And they looked at 5 different ways this could work. 5 supply chains.
That's right, 5 configurations. It's worth quickly outlining them because understanding these options is really key to understanding the results.
Okay, lay it off for us.
First up, full domestic production. Pretty straightforward. Everything happens inside the European country. You make your green hydrogen locally, use it for HDR, process it in an EAF, all within, say, Germany.
All in-house.
Right. Second, import of green hydrogen. Here, the hydrogen gets made somewhere with potentially cheaper renewables. The study used Morocco or Chile as examples.
Okay.
Then you transport that hydrogen all the way to Europe. The steel making itself, the HDR and EAF steps, still happens in Europe, just using imported H2. And they looked at pipelines for Morocco or shipping liquefied hydrogen LH2 from Chile.
Shipping hydrogen sounds tricky.
It is. Definitely has pressed implications. Third option, import of hot briquetted iron, or HBI. Yeah, this shifts the first big step, the iron reduction, outside Europe. So you take iron ore, reduce it using green hydrogen in that low-cost place like Morocco, and you make HBI. It's basically a stable, easy-to-transport form of the direct reduced iron, the DRI.
Oh, okay, so you ship the reduced iron, not the hydrogen.
Exactly. Then that HBI gets shipped to Europe and fed into an EAF here to make the final crude steel.
Okay, makes sense. And the fourth?
Fourth, full import of crude steel, CS. This takes it one step further. The entire process, reducing the ore with hydrogen and making the crude steel in an EAF, happens in that low-cost location, like Morocco in their model.
So you just import this finished steel slab or billet?
Pretty much, yeah. The final crude steel product gets shipped to Europe. They did also look at a fifth option, a mix of HBI and CS imports, but these 4 capture the main distinct routes.
Got it. And to compare these, you mentioned they calculated the levelized cost of crude steel, LCOCS. Can you quickly break down what that actually measures?
Sure. LCOCS, levelized cost of crude steel. It's similar to LCOE for electricity or LCOH for hydrogen, terms you might have heard.
Okay.
It's essentially a way to figure out the average cost to produce 1 ton of crude steel over the entire lifespan of the steel plant. It bundles everything together: the upfront building costs, running costs, maintenance, raw materials, fuel like hydrogen or coal, and really importantly, the cost of energy, especially electricity.
It gives you an apples-to-apples comparison.
Exactly. By levelizing the cost over the lifetime output, you can compare very different technologies and these different supply chains using one consistent number. And they projected these costs out to 2030, 2040, and 2050.
Okay, that makes sense for comparing options. So let's get to the juicy part. What did the study actually find? What's the bottom line on the economics of green steel?
Well, here's where it gets really interesting, but there's a huge if attached. The study projects that, yes, green H2-based steel can actually compete on cost with the old coal-based BF plus BOF steel, maybe as early as 2030.
That's soon.
But, and this is absolutely crucial, that only happens if you have effective carbon pricing in place.
Ah, the carbon price.
Yeah. The study assumed a carbon cost of 135 euros per ton of CO2 kicking in from 2030 onwards. Without that significant price tag on emissions, the old, dirty BF plus BOF route, it stays the cheapest in quite a few scenarios, like for domestic production in Finland, even looking out to 2050.
So policy really matters here. Carbon pricing is foundational.
Absolutely foundational. Green steel likely won't outcompete unabated fossil steel on cost alone without it.
Okay, so carbon pricing levels the field against the old tech. But among the green options, which supply chains come out cheapest? And does it vary by country? Let's start with Germany, the biggest producer.
Right, Germany. For them, the study found making hydrogen locally using German renewables was kind of competitive with importing hydrogen if it came through hypothetical large pipelines from Morocco.
Large pipelines, okay.
But importing hydrogen from Chile shipped as liquefied H2, that was consistently the most expensive import route. Just too much cost tied up in liquefaction and long-distance transport.
Right, that transport challenge again. What about importing the intermediate product, HBI?
Importing HBI from Morocco looked pretty competitive for Germany. Roughly neck and neck with making HDR steel domestically in Germany, maybe slightly cheaper, around 90% of the domestic cost in 2030, perhaps a bit lower by 2050.
So HBI imports look viable, but what about going all the way and importing the finished crude steel for Germany?
Yeah, this was maybe the most striking result for Germany. Importing the full crude steel, made in Morocco, consistently came out as the lowest cost option.
The cheapest overall.
Yes, throughout the whole period they modeled. It was projected at around 89% of the cost of German domestic HDR production in 2030, falling to about 84% by 2050.
Why such a big difference?
It really boils down to the projected cost of electricity, the LCOE. Morocco's renewable electricity cost is projected to plummet, thanks mainly to solar, down to just 10.2 euros per megawatt hour by 2050 in their model.
Wow, 10.2 euros.
Compare that to Germany's projection of 22.3 euros per megawatt hour in 2050. Since electricity is the biggest cost driver for making green hydrogen and also for running the EAF.
Right, it dominates the cost.
Exactly. Producing where electricity is dirt cheap makes the final steel product significantly cheaper, even after you factor in shipping costs.
Okay, that's a massive difference in electricity costs and clearly tilts the economics. What about Finland then? Northern Europe, different renewable picture.
Yeah, Finland's results point in a different direction for domestic production. Making hydrogen locally in Finland looks generally more expensive than importing it via large pipelines from Morocco, or even shipping it as LH2 from Chile, especially early on.
More expensive domestically, why?
Primarily due to a higher local cost of electricity for hydrogen production in the model, particularly in the early years, 38.4 euro MOLs in 2030, quite a bit higher than Spain or Morocco.
Okay.
So consequently, the study shows both HBI and crude steel imports from Morocco are noticeably cheaper than trying to make it all domestically in Finland. HBI imports are projected around 90% of domestic costs in 2030, down to 85% by 2050.
And crude steel imports.
Even cheaper relative to domestic, something like 83% down to 76% of domestic costs between 2030 and 2050. It strongly suggests Finland might be better off, economically speaking, becoming an importer of green steel or HBI rather than a primary domestic producer.
So for both Germany and Finland, importing looks economically compelling, driven by lower electricity costs elsewhere. What about Spain? You mentioned their great solar resources.
Spain looks like the star pupil for keeping the whole chain domestic, purely based on cost.
Ah, interesting.
Their fantastic solar potential leads to the lowest projected levelized cost of crude steel among the 3 countries studied. It starts around 440 euros per ton in 2030, dropping quite significantly to 351 euros by 2050.
So domestic production in Spain is competitive.
Very competitive. It's competitive with, or sometimes even lower cost than, most of the import options for Spain. Even importing crude steel from Morocco, which was the cheapest for Germany and Finland, is very close in cost to Spain, making it themselves somewhere between 96% and 100% of the domestic cost over the period.
And that's driven by Spanish solar getting really cheap.
Exactly. Their model sees Spain's LCOE dropping dramatically as solar takes over, down to maybe 14.4 euros per megawatt hour by 2050. Super competitive.
Okay, so let's try and synthesize this across the 3. It seems like transporting hydrogen itself, especially as liquid, is expensive and might not be the best bet.
Yeah, the transport costs really bite into the savings from cheaper production elsewhere.
But shifting the actual production, making the HBI intermediate, or the final crude steel, to places with super low renewable electricity costs, like Morocco in this model, that seems to offer real cost savings for the importing country, especially for Germany and Finland.
That's the core takeaway on the supply chain comparison, yes.
If we think about the bigger picture for Europe, These findings have some pretty profound implications, don't they, for energy, for industry strategy?
Absolutely. Take the EU's hydrogen strategy. It relies quite heavily on the idea of importing hydrogen from places like North Africa.
Right.
But this study puts a question mark next to that, at least for steel. It suggests that while making the hydrogen might be cheapest there, the cost of getting it to Europe could be so high that it makes more economic sense to just import the thing made with the hydrogen, the HBI, or the crude steel itself.
So maybe H2 imports won't be the main driver for greening steel production inside Europe, but rather enable imports of green steel products.
It raises that possibility, yes. It suggests the economic logic might favor importing the product rather than the energy carrier for this specific application.
Which brings us to the pros and cons of importing HBI or crude steel. The pros seem clear from the study: potentially lower costs for countries like Germany and Finland to get green steel.
Right. And it also lets Europe leverage its existing strength in electric arc furnaces. We have a lot of EAF capacity already, perfect for processing imported HBI or melting down imported crude steel along with scrap.
And are there benefits for the exporting countries?
Potentially big ones. Building HDR plants in, say, Morocco to make HBI or steel for export directly boosts their own energy transition and industrial base. It could shift trade pattern. Instead of just exporting raw materials, they export higher value, intermediate, or finished goods.
And maybe strategic benefits for Europe, too, diversifying suppliers.
Could be. Replacing fossil-based imports from current sources, some may be less reliable, with green steel imports from new partners could enhance supply security.
But there's always a but. The clear potential downside for Europe is jobs, right? Especially in regions that currently do the primary steelmaking, the iron reduction part. If we start importing HBI instead, what happens to those jobs in that capacity?
That is the major social and economic question, absolutely. It's a huge concern for policymakers in those communities.
Yeah.
Now, the study does briefly note that the initial iron reduction step often employs fewer people than the later steel processing stages. So one argument could be that importing intermediates might free up capital in Europe for higher value parts of the chain or other industries.
But that's a complex transition.
Extremely complex. And the study acknowledges it didn't fully quantify those wider economic impacts beyond the LCOCS comparison. It also didn't model, for example, Spain using its low cost to supply HBI or green steel to Germany or Finland, keeping more value within the EU.
Intra-EU trade, right?
Exactly. Or look into other emerging tech like electrowinning. So these are areas needing more research for the full picture.
And that's really key because the EU talks a lot about wanting to keep steelmaking capacity and support the industry here. It's a massive employer, 2.6 million jobs linked to it? Huge economic contribution.
It's around 140 billion euros in gross value added, yeah.
So these findings, they really highlight a tension. The pure economic efficiency logic might point towards importing green products from the cheapest renewable locations.
Like North Africa in the model.
But that could clash directly with the goal of keeping the entire value chain humming within Europe.
Precisely. So this study, Towards Defossilized Steel, Supply Chain Options for a Green European Steel Industry, it paints a really clear but also quite challenging picture. Yes, green steel looks techno-economically viable, possibly soon.
If carbon pricing is strong enough.
Crucially, yes, policy is essential. But within that green transition, the cost dynamic strongly suggests we might see a geographic shift in where certain steps happen. Local production looks good for places like Spain with top-tier renewables. Right. But for others, like Germany and Finland, importing intermediate HBI or even the final crude steel from regions with potentially ultra-low renewable costs looks, on paper at least, economically very attractive.
Exactly. And that just opens up these fundamental questions that go way beyond the cost per ton. It's not just about spreadsheets, is it?
No, not at all.
It's about energy security. Who are we relying on for our steel? It's about industrial strategy. What bits of this process do we want to keep in Europe? It's about jobs, who wins, and who might lose out in this massive shift. And it's about Europe's whole relationship with trading partners, especially in the global south, places with amazing renewable potential.
Which really brings us to a key question for you, our listener, to ponder. If importing green steel products, say from Morocco, is projected to be significantly cheaper, how should European policymakers, how should companies balance that powerful economic pull against the very real desire to keep steel production capacity and the jobs that come with it strong here at home? What's the right blend of investing domestically versus embracing international trade for Europe's green steel future?
A lot to think about. Definitely. We've really just scratched the surface here, drawing on the insights from this one very detailed study. But hopefully this deep dive has given you some key perspectives on the complexities, the economics, and the potential future geography of green steel, and maybe, hopefully, spark some curiosity to explore even further yourself.